So now we are going to look at limits at infinity and the interpretation in terms of horizontal asymptotes. This is about the end behavior, if you want, of a function or its graph. So let's look for instance at this function. You see that when x becomes large or negative large, the function seems to level off. And here you see that if we draw the horizontal line y equals 3, it seems that the graph of the function gets closer and closer to this horizontal line at the far ends of the graph, so to the right and to the left. Let's take a look at what happens for x growing on the right hand side of the graph. Let's zoom on this part of the graph. So let's pick an x and the corresponding point on the horizontal line y equals 3 and the corresponding point on the graph of the function. It has y coordinate f of x because of course this is a point on the graph of the function f. Now if x grows, you see that the y value of the point on the graph of the function becomes closer and closer to 3. So in other words, the values f of x are getting close to 3 as x grows, and this x going to plus infinity is going to be the notation we use to indicate that x grows without bound. Symbolically, we're going to say that the limit when x is approaching positive infinity, meaning when x grows, of f of x is 3. This symbol indicates that x grows without bound. Now graphically you see that that means that the graph of the function is getting closer and closer to the line y equals 3 on the right hand side of the graph. Now on the left hand side we can look at what happens, and we have the same behavior. The graph of the function is approaching this horizontal line. Symbolically, we're going to write that the limit when x is approaching negative infinity of f of x is 3. That indicates that when x becomes more and more negative large, the values f of x get closer and closer to 3. So this is the symbol we'll use to describe the end behavior of the graph on the left-hand side. So in terms of formal definition, we will say that the limit of f at positive infinity is L if the values of f of x can be made as close to L as we want by taking x sufficiently large. So making the values of f as close to L as we want means for any specified distance epsilon, we can make f of x within epsilon of L. By taking x sufficiently large, that means by making sure that x is greater than a specified value. So formally this is how we would translate this definition. Of course we have an analog definition for the limit of f at negative infinity, and we'll say that this limit at negative infinity is L if the values of f of x can be made as close to L as we want by taking x sufficiently negative large. And in terms of analog of the epsilon delta definition, this is what we would get, that the limit at negative infinity is L if for every epsilon there is a positive m such that f of x is within epsilon of the limit L, provided that x is less than negative m. Graphically, this is interpreted by saying that y equal L is a horizontal asymptote of f. So this is going to be the case if the limit of f either at positive or negative infinity is L. In that case, on the corresponding end of the graph of f is going to get closer and closer to the horizontal line y equal L. In this particular case that we looked at the beginning, y equals 3 is an asymptote to the graph on both sides because the limit both at positive and negative infinity for that function is 3. Now we're going to move to the next video to see how to find these horizontal asymptotes and these limits at infinity.